Yeah, my name is Rafael. I work here at CSCS, I was saying. And me and my colleague Rocco, we're going to be teaching these 3 days in the course. And now, before going to the content, let's go a bit through the agenda and information that I put in Slack. So we're going to start now. I will elaborate more later, but with a very, really simple introduction. Sorry, I think it's making noise, this thing, when I move? Sorry. We're going to start now in these 2 hours before lunch with a really very simple introduction to the topic. We're going to focus in training and training models, and afterwards in the afternoon, Rocco is going to start with the more like more realistic deep learning problems and lessons, and it's going to be about convolutional neural networks for computer vision. And then tomorrow, the day, you will start with learning more on, say, like good practices and tips and tricks and things good to do for training networks. And then in the afternoon, Rocco will show you again. It will be about generative models, like to generate images and things like that. And so the whole day is going to be with Rocco. And then on Friday, the whole day is going to be about natural language processing, and we're going to learn about the transformer models that are very popular now. And we're going to do some tutorials. That's it. So this is pretty much what we are going to do. Everything should be like very basic, and we're going to use PyTorch in the way, and we will try to explain maybe we won't give an overview of PyTorch, but we're going to try to explain what we are doing so you can learn also PyTorch in the way. Okay, so all of you have the course accounts that you got. So these course accounts, please use it for the course. Then, do we have the material? So I cannot. So the material is posted here in Slack. You can clone the repository, and if you do so, when you do so, please go to Scratch, because if you clone it in home, there are things that may not work in that file system. So just to have everything nice in Scratch working, just do it there. And the rest, we're going to be working with Jupyter Lab. And Jupyter Lab, you can go to this. Maybe I can use this now. Yeah, here this Jupyter CSCS.ch, and inside, so when you log in, actually I can show you quickly. You can get a terminal, and there you can run this command. Just copy and paste this. And this is going to create a kernel. Kernel is just the backend for Jupyter, and that is going to have all the software that we're going to use during the course installed. And then afterwards, maybe you need to wait like a minute or 2, but it should appear. No, sorry, it should appear here if you. Okay, it should appear here. Okay, select kernels. It's called ML 2024. And also, I won't show it because I have a bunch of things in this is my account. But here you can navigate to different, to browse the files. And this script also is going to create a Scratch link that you can go to access through here, through the notebook, the Scratch file system, and go to your notebook. To the material. And what else? I think that's everything. And for Jupyter, here we posted. So what you have to do to get the notebook. So here, please, so you have to click here in Advanced Options, and then Advanced Reservation, and you write DL PyTorch, because if you don't put it, you may have to wait a lot to get the notebook. And here in time, put just enough time for the whole day, so it doesn't stop mid-exercise. So So right now we're not going to work with a notebook, so we will use it like in half an hour or so. And so if you want, just start it and let it there to start. And I think we can go and start the presentation. All right, I don't have to. Yeah, okay. So as I said in the morning, now sorry, in the morning, 2 minutes ago. Now we're going to focus on something. We're going to use a very simple data and very simple models, and we're going to try to focus just in how the learning of a deep learning or a machine learning model works. And so we decided to do it like that just to do not complicate talking about neural networks and also about training neural networks at the same time. So we are going to consider a data set, this data set, and well, this is just a schematic representation, of course. So here, sorry. Sorry, I'm having a bit of trouble with this and yeah. So so in machine learning, so often, well, all the time we have the data, and often we have a question that's something like this, that is, so now we have all these points x, y, and how can we can find a value of y for an x, for any x here, so an x that is not in the data, okay? And to do that, what we do is to train a model to learn from this data. And what does that mean? So what it means is just you select a mathematical function or a neural network, or yes, a mathematical function in general that has parameters. So and parameters is values that you can adjust, so it can describe the data. And in this case, if we go back here from the type of data, and as I mentioned, it's very simple. We see that maybe with a linear model, just a line, we can describe it well. And let's say that for the kind of problem that we want, maybe if the line, let's say that goes here in the middle, the error that it's going to give us is not that bad. So it's accurate enough for us to use it. Okay. So we start then with a model, and this is the simplest model that we can come up with, and it has these two parameters, m and n. And now our problem is that how can we use this data, so all these points that we have, to find the values of m and n that better or that predict the y's, that explain the data with enough accuracy for us to use. Okay. And for that, what we do in machine learning is to find a loss function, right? I'm putting everything in red. It looks like for kids or something, but the idea is to, like, vocabulary and concepts that I want you to pay attention, and also for me to remember to talk about them. So instead of listing them, I just put them in red. So we find a loss function, and a loss function is just a mathematical function that depends on these parameters and depends on the data, right? And the idea is, so we construct it in a way that it shows the error of the predictions of the model predictions with respect to the data. So in this case, what we do is so yi hat is so you put an x in the model, and the value that it's going to give is just predicted values, and yi are the data. So we get all the differences between the predicted values and the values from the data. We average them, and we get a loss function. And the thing is that now this loss function, we can minimize it. So if we have an algorithm to minimize this function with respect to m and n, to the model parameters, then m and n is going to be changed until it gives a good representation of the data, or at least that's the idea. And so here we can this part you don't do it in practice, but I want to show you that we can replace y by m and n, sorry, by the model, and now we see we have xy, yi, and the m and n, and this is all what the loss function depends in. So if you replace here all the data points, so they are not just numbers, then what you get is a function of m and n. Okay, and this process of minimizing the loss is what is called training the model. Okay, and so let's go back a second. So this function here, if we plot it in, say, contour plot with, this is loss. So loss, you know, these are contours. Is like the loss is like coming out of the screen, right? And then you have sorry. Then you have m and n, right? So this axis m, this axis n, and you know, in contour plots, the closer the lines are, the more steep it is, and the farther it means that it's getting flat. So this is I shrunk it like it looks like circumferences, but they are actually like a parabola, and they are like in this shape like this. Okay, is it clear until now? Yeah, and so how it works is we start with a random value of m and n in our model. So we initialize the model in our script, and it gives some random value. And this, of course, is going to give a random line that it doesn't describe the data at all. And what we do now is to find an optimizer that will take these two parameters from this random place that it was all the way in the loss surface to the minimum, or to a minimum. Okay, and now this the line is going to move from something random to something that is going to explain the data. Okay, and so we can continue. So this one, just with more detail, how it happens is like this. So the first step is that so we get the loss function, and we evaluate it on, let's say, on the whole data set, and of course for, again, random values of m and n, and this is called forward pass. So evaluating the loss function. So it's just put the values on the model and get the loss is called forward pass. And then once we have the loss, we can do an algorithm that I'm going to talk about right after this. It's called backpropagation. That what is going to give you as a result is all the gradients of the loss with respect of the parameters of m and n, which I wrote here as w, because parameters sometimes in deep learning is also known as weights. Okay, so you evaluate, you get the gradients with respect to m and n in the backpropagation, and then finally you can use these weights these gradients to move in the surface loss. So if we go back again, so we start here, we evaluate, we get some value of L of loss, we get the gradients, and remember the gradients are always in the direction going down in a surface. Okay, so and because of that, we can use it to move in the surface in the direction that minimizes the loss. Okay, and there is here normally you don't use just directly the gradients, you multiply it by another parameter that is called learning rate, and the learning rate here, as you see, is pretty much the size of the step. If you put a big learning rate, it will move big steps. If you put something smaller, it's going to go very slow. And we're going to discuss more about it in a bit. Yeah. So then the idea is you do that, and you repeat it and repeat it and repeat it until this so m and n arrive to to a value that gives a loss that you start seeing converging. So you may see something like, if you plot the loss with respect to the steps, you may see something just going down like this, exponentially sometimes. And we will see, we'll play with it now in the notebook. So this is about backpropagation. So an important thing in machine learning is that this calculation of the gradients for the minimization. Sorry, by the way, I didn't mention. So this algorithm is is used outside deep learning. It's called gradient descent. It's an optimization algorithm that take advantage of the gradients to move in a loss surface. Okay, or in anything that you want to minimize. Okay, so something important in deep learning is that these gradients are not computed numerically by 2 points and getting the distance and dividing, and it's not also symbolically. It's calculated with something called automatic differentiation. And in the afternoon, if we have time, Rocco prepared an extra notebook, bonus notebook, let's say, that we can show actually how it works. But the idea is that during forward pass, so this one is very simple. It's just mx plus n. But imagine that you have like a very large model with many operations. All the operations that you do to evaluate the loss, they are recorded, and also the derivative of the operations are recorded. And in the case of mx times plus n, let's say for a value of x, let's say you have all of them, m and n are 1, and then x you evaluate in a number that is 1, then you get m times 1 is 1 plus 1, and this is the value of this is going to be passed to the loss, and then the derivative of this operation is also going to be registered. And in this case, the derivative is going to be m only, because n. Sorry, the derivative with respect to m and respect to n. The derivative with respect to m is just x. I'm sorry, and then evaluated in 1 is just 1, so a number, and n derivative is 0. No, sorry, it's 1. And then at the end you get a number for the derivative and for the loss. And if you have many operations, like in a long neural network, these operations, you can stack them through the chain rule of calculus, and you have all the values. So you write the f, the x, the whatever, and then at the end it will give you a value for the whole long operation that you did of the gradients. It's a bit hard to understand, but maybe we'll have time to play with it later. But the main point is that it's exact. It's not an approximation of the derivative. It wouldn't be possible, I think, to do machine learning with approximate derivatives. And that's the main reason why PyTorch, TensorFlow, and JAX, they are deep learning programs, because they provide this feature of automatic differentiation. Anytime you do operations in something that you can define in these codes as parameters, they will record all the derivatives and all the operations. So afterwards you can do like gradients or dot backward or something like that, and then you get the gradients of the whole operation that you did with respect to the parameters. Okay? Okay, if we can continue. Okay, so if we repeat the steps that we did that I mentioned before, and we are evaluating the model in all the full data set, you may see something like this. Like through all the gradients, there is a path in the loss function that goes to a minimum, or in this case there is only one minimum. But in practice, we don't evaluate the model in the whole data set for every step, because for one, the data set can be really large and just doesn't fit in memory, so you cannot do this operation. And also sometimes you want some oscillations in the minimization, so you can jump minima. And this is achieved by evaluating in smaller batches, so batches of the data. And there is a parameter of it's called hyperparameter. It's something that you have to define in advance. It's called the batch size. And in general, if you use the whole batch size, you may get something very soft. If you use like one by one, this is the extreme case, you get something very, very chaotic in the movement, in the path through the loss function. And in this case, this is a variant of gradient descent that is called stochastic gradient descent. And most of the cases, what is used is something between that is not one and is not the whole training set. That you get something oscillatory but more controlled than this thing so chaotically. And this one is called mini batch stochastic gradient descent, which is mostly what we always do. With this introduction, I think we can go to this notebook if you have already the material. SGD is the directory SGD, linear model SGD is the only thing inside of this directory. And we're going to play with different parameters to get plots like these ones. And the point of the notebook is to understand the role of the batch size and the role of the learning rate, and also that you see how how the training happens and all the steps. So, and now I'm going to quickly go through the notebook, and then I will leave you some 20 minutes or, I don't know, some time for you to play with it, and we can discuss individually, okay? So, I will sit down because... is it fine here? Okay, so the notebook is inside SGD, so PyTorch training SGD, linear model SGD, okay? So if you haven't gotten the notebook running yet, wait, maybe you all have the notebook running yet, or no one? Okay, maybe wait 5 minutes, and so you are not looking at the notebook, and wait 5 minutes and just get it. Just remembering Slack, I can put it here. So I will introduce the notebook quickly. So this notebook is just pretty much the same things that we discussed before in the slides, but now we're going to do them in practice and see how it works. I'm going to do a run, and then I let you play with it. And in the meanwhile, I will explain some PyTorch details. So here, the first things that we're going to do is to create the data, and the data, as you saw from above, from before, is it's like a line, it's a linear kind of data with some noise, and this is what we're going to do. So in PyTorch, there is something called torch dataset that we imported before, and you can create datasets by creating a class that inherits from it, and then you modify, you define get item, that this is going to be called anytime an iterator iterates over it. It will return whatever you define in get item. The size is fine, and len, that len is going to give the size of the data set. Okay, this is going to be relevant later. And in this get item, to generate our linear fake data, what we do first is we use this to generate a random float from -0.5 and 0.5, and then we get this one and we put it in a linear model. No, it's a linear equation shape to generate a y that is a line with respect to it. And you see that this slope and this offset, we define it here, so we set how the line is going to be. And then we create some random noise and we add it. And then in getItem, we return the pairs x plus y with noise. So anytime an iterator iterates over this data set, it's going to give a random x and a random y, but it's linear somehow with respect to x plus some noise. Is it clear what is the data? And if you have questions, please just. Yes, for the video, otherwise.
Yeah, my question is, why do we need the noise in this case, and how we define the noise with respect to the range in which our X data set is in?
Okay, let me show it. I will show it now. Yeah, good question. Okay, so let's see how this data set works in practice. So we instantiated here, and now we have a data set. And now we need to create an iterator for this data set. This in PyTorch is called data loader. And we pass the data set, we call train set. So we set things like the batch size that I mentioned before. This is the amount of data that we're going to use to evaluate anytime that we evaluate the model. You can do things like, shuffles, and this drop last is if the batch size, if the data set size is not a multiple of the batch size, so it will be like 128, 128, blah, and if at the end it gives like 3, this drop last means that don't use this one. Just use everything that's multiple of 128. And so we started. You can create also like multiple workers and prefetching, so to put data in the GPU before in advance and things like that. All that with the data loader. And so now we have the data loader, and we can iterate over it like you iterating any iterator in Python. And if we print, so here I put the shapes. We have 128,1, that's the 128x, so values of x, and 128 values of y. So they are pairs. Anytime you iterate, you get these two pairs. Okay, clear? And so now we can see the plot. And so answer to your question about the noise. So the noise, we actually, we don't need it. So if we remove this noise here, what happened now? Sorry, I think there is something with Jupyter, not to. Could you ask if, thanks. Sorry, apparently this is something with Jupyter. But anyway, I think I can explain. So if you don't put noise, you just get a line. And I just added noise to make it look more like real data, but there is no reason. And also for the, I think a line maybe would be maybe a couple of steps. It would very quickly fit it, and I want to do something more complicated to make more sense in the iterations. Okay, I will continue without running, and I'm sorry about this. Okay, try. Okay, so you saw the data. I deleted it on top of everything. And so the rest, so at this point we have the data set, and we have an iterator. We can iterate over it. And I forgot, so I put here just 1,500 samples, and we are going to iterate right now in batches of 128. So the next that we do is exactly the 3 steps that from these 3 steps from the slide. sorry. Ugh. Sorry, from here, no. We get a model, we get a loss function, and we get an optimizer. And so the model is the part more complicated. We use the same API that Torch gives to create neural networks, and we're going to discuss it after this notebook. But this is we create here a matrix, and 1 and 1 means that it's going to have a matrix of 1 by 1, which is M, just the linear model, and automatically with this there comes an N that is called bias. So in practice, what we are going to have here is a model. We have an M, let's say, that is called weights, and times the input plus model.n. So this is what this is the operation that we are doing here. So it's the parameters that we're defining. So we define a parameter m and parameter n with different names internally, but this is what we did here. And we get the loss function. MSE is a mean square error. It's the same loss function that we have here. And an optimizer, we're going to use stochastic gradient descent, which is what we saw in this slide. So it would be, in practice, it's going to be a mini batch 1 because we're going to set a batch size 128. And yeah, so we select this, and here you see that it says device equal device, and device is 0. It means that it's going to copy the model to the GPU, so to the GPU 0, to the first GPU, though we have only one. It seems to be working. Yeah, maybe just can... to the GPU.
If we run it on a CPU, no, will it just run on the CPU as well?
If you let the two device 0, no, it will complain. But if you remove all the two devices, I think in general you can write something like device equals 0 if there is GPU, otherwise CPU, and I think it knows and it won't do any copy. I'm sorry. Yeah, I can show you in my laptop. No, I have it locally. I don't need the GPU actually. So I'm sorry about this. Yeah, I will show you in my laptop. Okay, so data set, data loader. Here we show, I put 8, sorry. So we have the data, here -1 to 1 the y, and -0.5, 0.5, and we added some noise. It looks like that. In my laptop I use MPS because of the Mac, but so imagine that we have a 0, the GPU 0, but the rest is going to be the same. So we define the model, we move it to the device, to the GPU in your case. We define a loss function, and we define an optimizer. So this is just for logging, for plotting later. It's nothing to do with the training. And we arrive here to the training. We arrive here to the training, and so there are two loops. One loop, so if we start in the internal loop, one loop is over the data loader, and this loop is going to stop when len, which is 1500, when 1500 samples have been already taken from the data set. And after that, if you iterate again over it, it's going to start from the beginning. All right? And and we have nested this train over the data set inside another one called trainings over epochs. And epochs is how in machine learning they call a full run over the data set. So anytime you repeat the data set, you go to the beginning. This is called an epoch. So we decided here, put 2 epochs and train the data set, the size of the data set. And now, this one, I just put it here because since we are generating random data, if we don't restart the seed of the random generator, there won't be epochs. They always will be different. So we do this one to always have actually real epochs. So after a full run over the data set, it starts from the beginning again. Okay? Again, if there are questions, feel free to interrupt me. So this is the training loop. This is what happens. The first thing that we do here is optimizer, that is stochastic gradient descent. We do zero grad. And this has to do with the automatic differentiation. Remember that I told you that every time that you do operations in PyTorch, it will record all the derivatives. And this is a way of telling, start a new record of derivatives from scratch. Because if you don't do that, anytime you loop, it's just going to plug all these derivatives, and then you're going to get derivatives from the previous iteration, and this is not what we want. We want is to do one forward pass, get gradients, and then the next iteration start from the beginning, a new forward pass and new gradients. Okay, so this is what this means. The next, we evaluate the model in the data, and remember that the model is in the GPU. And since the model is in the GPU, then the data needs to be moved to the GPU as well. And you do that in the same way we did for the model to device. X to device is going to go to the GPU. All right. And now this is going to give you y hat. So y hat is how I call the predictions. So it's a predicted value. And now we have y hat and y from the iterator, and we get the loss. So we evaluate the loss function, and we get the loss value, and we compare the predictions with the reality, with the data. And here you see that y was sent to the GPU as well. This is nothing to do with it. This is just to plot later. So this is just nothing to do with the training. So now we have the loss. This is called forward pass, remember? And now we do loss backward, and this is the backward pass. After this line, now the gradients are going to be computed, and they are going to be like, the optimizer is going to own them in PyTorch. And afterwards, when you do optimizer step, you do this, right? It moves and updates the data. And so using this expression. And here I forgot to mention that in the optimizer, when we define the optimizer, we put learning rate 0.1. This is going to be the size of your step, of the step of the algorithm. And this learning rate and the batch size, so those are they are not like parameters of the model. They are called hyperparameters. That are the model depends, the training depends on them, but you have to set them in advance. The other the parameters of the model they are called as learnables because they start as random, and during the training they are find out. So you want to ask a question or? Okay, this was clear. The training step. The training. Okay.
Why not 0.2, 0.5?
You will play with that, I think, late here in the notebook and later today. But yeah, this one, I think I will explain later and you will see better. So now here we log all the values. So weight is m, bias is n, and loss, where's the loss? And now we can plot. And we get something like this. We did very little epochs, so this is not really converging. So I'm going to start from the beginning. I will restart the model. We go back to random numbers, and I will put here 5 epochs, and let's see what happens. Okay, now it looks more like converging. I will restart the model again. and I train. Oh, I left the same amount of epochs. Let's put 10, see what happens. Okay, it started to converge. Okay, and you see here, well, maybe we will see later what this means, but all these peaks. But here you see that this is the initial step, how the model started with the random m and n, that this gives this line that has nothing to do with the data. And now it moved, and now it's starting to look more like the data. I think maybe if we put a bit more epochs, I mean, since if it is so quick, maybe we can put 20. And now, so we started from a different place, and we see now that it's almost on top. It's pretty much what we want. Maybe we can do better, but we see here that we are starting to, the minimization started to converge very nicely. And in practice, this side here, you never have it. You know, well, you can have it actually, but I don't know, in some problems you cannot just do this plot and look the line on top of the points because it's very complicated, and many times, most of the time, it's high dimensional, so you cannot really plot it. So what you look is at this, and in tomorrow with Rocco you will learn to interpret this curve, and sometimes it does things that may be strange, and you will learn to understand what is happening with them. And finally, the last plot. We have what we saw in the slide. So this is the loss function. Offset I call n, and slope is the m. And here we see I put with an x the minimum. And here we can see the path, how it moves. And you see, maybe I can create a new one to see if because to show you from the beginning. What happened? It looks pretty much exactly the same. Gosh. Okay, this one is more. Here you see, so it starts, let's say, something around here. And you can see here how it moves perpendicular to the contour lines. So the contour lines are, I don't remember this is exactly the general name, but like equipotential. So they're constant. So by definition of the derivative is perpendicular to this constant lines in the surface. So it's always perpendicular. And then it goes all the way to the minimum. Okay. And now I think I can leave you play until let's say 11:15, 11:20, and we can pass and we discuss if you have questions. But what I would like you to pay attention is to try different batch sizes. And see how try to understand what is the effect of changing the batch size on the stochastic gradient descent. Sorry, and this is a very, let's say, good opportunity because in general, when you have large models, you cannot see this plot because it's just too high dimensional. You cannot plot it. There is dimensionality reduction, and you can kind of project it in a smaller space, but it's not the same. Here you're seeing exactly what is happening, and that's why we chose such a simple model, so you can see this. So pay attention to what happens to the different batch sizes, and if you can, how the learning is organized. And also, you can give it a try to different learning rates, and you can see actually. So your question, what happens? But as a preview, if we you see the number. So this one is 0 to 1. If we put learning rate 1, it means that the value of the derivative that we calculated here, for instance, this point is going to be multiplied times 1. So the updating step may be something really long. Actually, we can do something before I let you alone. Let's put here Well, 1. I mean, it's a bit exaggerated, but let's see what happens. So the plot is gets very jumpy, and this is like, maybe we can put the dots and see what happened. This one. Yeah, it advanced really quickly. And so you see this one. They are always perpendicular, but they are really long. And maybe it can make the convergence can affect it. And in practice, one of your goals is to make this convergence as fast as possible. Because let's say that if you have time at CSES for your big model to train them, and you chose learning rate 1, like in this case, maybe you won't get a convergence as fast as with a better value. So you will lose a lot of time training. In this case, it was seconds, but sometimes it can be weeks. And so in practice, you start. I think maybe with time, when you start doing it, you can get for your problem an idea of what makes sense in terms of learning rates. But being a hyperparameter, you have to try many and to choose the one that converges faster. And you do like test runs, and then afterwards you find this one converges faster, and then, okay, I will do the rest of my runs with this value. And there are also techniques like to start with some educated guess, and then to change it adaptatively. So PyTorch does it, so it speeds up the convergence. Okay. And okay, so play this with these two things, and yeah, we can pass by the tables, and yeah, pay attention to these two things.
When you use different batches,
Sorry, just for the.
the purpose of doing it in different batches, is it because if the data is really big, then doing one batch with the whole data set might cause memory problems? Or is it because, for example, if you had a multidimensional data set, by doing small batches, you are less likely to fall into a local minima or something of that kind?
Yeah, it's both things. So there is the practical part that sometimes you just cannot fit the whole model in at once because it's like terabytes or something. But yeah, one of the main reasons is to, like, when you have the batches, you start getting this randomness in the movement. And yeah, this is a very important point that I had left to the end. But so here we have only one minimum, and so it's easy. But in practice, when you have very high dimensional models, and if you have like other types of loss functions, there are so many. There are, like, it's like practically infinite local minima. So you don't expect to arrive to the global minimum. And having batch sizes helps with the possibility of like jumping local minimum and don't get stuck in one. So if you have the whole batch size, probably you will end in the first local minimum that you arrive, and you won't be able the algorithm probably won't be able to leave. So there are other techniques that you can do on top of that to escape local minimum, and there are things like random changes to other places. But yeah, this is one of the main points. Yeah, good. Another general question? Okay, then maybe we stop the recording and we can discuss through the tables. Yeah, we can discuss. I hope you had time to try all the options. So here, regarding the different batch sizes, yeah, you may have noticed that the total number of iterations. So the total number of iterations is always the number of epochs, the number of times that you pass by the data set, by the full data set, times the number of iterations that you get internally. Because when you change the batch size, if you put the full data set, you will get one iteration, only one iteration here, and if you put one, you will get 1500, and so it will change the amount of steps that you see in the plot and how the curve goes here. Also, we saw what happened very quickly with the learning rate. So if it is too big, then, so let's say if it starts in this point, as it happened before, the gradient is going to be in this direction, because the gradient is always perpendicular to the contour lines, right? To the isopotential, let's say, to the iso lines. So it will, if it is too big, it will come like to the other side. And so this one in 3D, it would be something like a basin. And if it is here and it's too big, then it's going to come to the other side. And then from here, it will, if it is like this, it will have to move perpendicular. So you will get this kind of zigzag thing that we saw. And this one maybe is not the most stable way that you want to do your training. So you have to try different learning rates until you are happy with the time to convergence and the error that you get. So that are the two important things that you need in your training. There are general questions, any questions about it that you would like to discuss? Okay, so then just to conclude, so we already discussed the first part, but I want to remind you again. In deep learning, when you use, so deep learning is about large neural networks that they have a lot of operations, and when you put all these operations in a complicated loss function, you get one of these surfaces like this that will have many local minima. And in training, when you're training a model, you're not expecting to find the global minimum. You're expecting to find a local minimum that is going to give you a reasonable error. Like you are happy with the error that you get for the kind of problem that you have, the kind of data, and then you don't care if it's a local minimum or it's a global minimum. First, you cannot tell. And second, if you get the good error, it's fine. And this problem that we saw here is called regression. And in deep learning, always we talk about two main kind of problems. One is regression, and one is classification. Regression is when you train a model to give you a real value, a continuous value. In this case, there was x and y, and we got a function that is just continuous. Classification instead is you train the model to give you classes, like if a picture is a cat or is a dog. Let's say there are two classes, and these models, they're a bit different in the sense that they give you. So you train them to give you the probability of the input, the picture of a cat, to be cat or dog. So it will give you 0.8, and you get two outputs, and it will be 0.8 and 0.2. And if class 1 is cat, that will be it's more probable that it's a cat, and it's not that probable that it's a dog. Okay. And these kind of problems, the classification and regression, they go inside of another umbrella that's called supervised learning. The supervised learning is the trainings that, so when you train on pairs of data, like a value, like in a function like with now, so x and y's, so a value of a function, or you train labeled data, like all these pictures of are cats and these pictures are dogs, and we have all the labels, and we compare. We try to predict a label, and we do the loss function comparing to the label that from the data. But there are other types of problems that is called unsupervised learning. That is there are no data, and examples there can be there are no labels, or there are no functions, just lumps of data, and there can be things like clustering, or everything at the end is kind of clustering, because it's somehow a way of finding groups inside of the data. Like, for instance, anomaly detection. So you don't have you have some signal, and you're not training to predict the signal. You're letting the model to find out what is, given all the data, what is unusual. And it will learn these kind of things. And this we're not going to work with unsupervised learning here in this course, but it is important to know. It's good to know that these two classifications. And there is also reinforcement learning that it came. I think. Well, I don't know if it came later actually, but it's a completely kind of different thing where there are like. This is like what is used sometimes for learning games, and that there are different players inside of the training, and there is an environment, there are interactions, and there are policies, and that penalizes actions that are taken during the training. And it's a kind of a more complicated thing, and it's kind of difficult, and we are not going to work with it here. And finally, something very important is that here we just train with the data set that we had. It was very simple, but we didn't do any testing or validation. And testing and validation is checking the model output, the model predictions for data that is outside of the training set, which is actually what you want. So you're not going to repredict the training set, you want to use it outside. And in general, when you're training, you may have this convergence here of the loss, and then time to time, I don't know, every epoch, let's say, you can do a check on data that the model has never seen. And you can see how also it converges for data outside of the training. Like if it is learning the data very well of the training set, but outside of the training is doing something strange or is not convergent, you have to take some actions, because this is what you are interested in real life applications. And I think, with Rocco you will have also exercises with that. And so it's almost 11:30, and yeah, so this is not the answer. Now I want to let's move to the folder MLP, to the directory MLP, and I want to show you some things more like in tune with the deep learning, like deep learning models, very simple, and so it's simple. So kind of a preparation for what you will learn with Rocco in the afternoon. And so let's start. Let's open I'm going to sit down because I'm going to be in the notebook, and so let's open 1A, MLP regression. So MLP stands for Multilayer Perceptron. That I think this is a name that comes like from the beginning of the research in neural networks, and it has to do with the similarity with the neurons in the brain, particularly this kind of pictures that we have here. And so probably you have seen this kind of schemes of neural networks before. I won't explain it because I tend to get a bit lost when I see it. But we made it, and I want to put it here so you can connect the dots with what we're going to actually explain. But to me, it's simpler to see it as the mathematical part, and I think for you it's going to be simpler to understand it. What is it, instead of trying to decode this image? Let's start with the regression problem, and let's make a very simple neural network to work with it. And this neural network is going to be a multi-layer perceptron, something like we see here, and now we're going to see what is it. So let's say that we have a data similar to this X and Y that we had before. Now let's say that our X is more realistic. It's a 784 multidimensional vector. This like the vector, the dimensions of the vector in machine learning in general can be things that make sense. As for instance, let's say that you want to predict prices of apartments, and you have like many columns, and one column can be the square meters, and the other one if it is in Zurich or not, I guess, and one if the things of the apartment, I don't know, the neighborhood, like numbers indicating different factors of the house, and each of them, they mean something. And here you can see it, this one like this. So it's a vector, and every of these dimensions they have some meaning, and this is called fissures or channels. this is how you call the dimension. So you can find these words there. So imagine that this is our data, and 8 is the batch size. So we have a batch of 8 and of dimensions 784. And we define this model. And so this is a very simple model, but the basic neural networks that are multilayer perceptrons have this structure, and they are just a repetition of these two operations: linear, which is just what we used before for the linear model, and for instance, this is ReLU, and it's called activation function. And so I will explain now one by one what they do. And see, we evaluate the model. And so we have these are all the parts of the model, of the layers. And if we evaluate here and we do shape, we see that it will give us a batch of 8, so the same batch that we use here, and 1. And this 1 is the output that we set here of the last transformation, which I will explain what they are. So seeing one by one. So this one. So So here we define the operations that the model is going to do, and here in forward is the forward pass. When you evaluate, it actually runs this function. What we see is that we pass x, the input, and we pass it to linear, to this FC1, which is this is what it's going to do is multiply it times a matrix and add a vector. So it's going to be exactly like, let's call it W times X plus a vector B, okay? And the size of this matrix is going to be 784 by 128. And this 784 in the first operation has to be the same dimension of the data. Otherwise, you cannot multiply it. And this first operation here is called input layer. They call it input layer, okay? And it has to, have to match the size of the input. And what it's going to do is just to project the input in a smaller dimension. Here I put 128. And it will add a vector. So it's going to project it and shift it. This is the operation what it's doing. And now we see, so we pass X and we get it here, and what we get, we pass it to this ReLU. And this ReLU is an activation function, and we can go to the model, to the notebook 2, and I can show you what activation functions are. Here we have many, so we have ReLU, like as before. I hate this error. And this one is just a function that you will apply it to the output of the linear transformation, the linear layer. And maybe we can start by having a look to this ReLU. So ReLU is X, so the same value that it has if it is positive, or 0 if the values are negative. And if we apply it here, let's say that we have a linear layer, and we create the same data, we apply it to the linear layer. And so then maybe I can just delete linear layer output. So the linear layer output is going to be, it's going to transform the vector. Here we have the 128. And if we add now the effect of the ReLU on the output of the linear layer, is this. Everything that was negative is going to make it 0, okay? And the reason to add this function after a linear operation is to introduce nonlinearity on the model, because if you don't have nonlinearity, so if you have is this. At the end, this is a succession of matrix multiplications. This is the same of a single matrix multiplication, and you just go your data, shift it, and project it somewhere else and shift it somewhere. So this is not going to give you learning capabilities. So the learning capabilities comes by having nonlinearity in the model. So so it can adjust to any kind of surface or or data. So is it clear? And so there are different options to choose. Sorry, for activation functions. Here, for instance, if we put leaky relu, you see here that now this is not really zero. It's not really zero. It can actually be negative. And the history behind it is that with this activation function, there are parts, like let's say rows of the matrix, that after doing the operation, it will give you always negative values. And then when you apply the relu, it's going to make it zero. And it's going to be like this. This part of the computation is not there at all because it's making it zero. And then to allow this one, let's say, to contribute to the model, leaky relu was introduced, and if you zoom here, you see that it's not really zero. It's a very small value. That is what we see here. We should have said before I show this part. Okay, so we can go back to here. And that's it. The rest is another linear transformation that you see 128 and 128, and it goes to 64. And finally, we add another relu, and after finally this 64 goes to 1, which is the output that we want. And as you may suspect, except this and this, these numbers are hyperparameters that you have to find out yourself for your problem and the amount of data that you have. You have to try different combinations. And the amount of operations that you do is also another, let's say, hyperparameter that it could make create more layers. Layers is anytime you do one of these linears and a relu, this is called a layer. And this is another hyperparameter. And yeah, so here we can see quickly what is the effect of we create a linear, same as we did before. And when we apply it, so before we have 8 by 784, and now the shape is 128, as we could have guessed here. And internally, the model have two parameters, weights, and if we do here, sorry, the linear layer has two parameters, weights, that is 128 by 784, which is what is defined here, and this weight is going to be the matrix for the matrix operation part, and there is bias that we can see. Bias is this guy here, the vector that you're going to add. And if we do here for one item in the batch, so in practice everything is vectorized all at the same time, but the operation would be input, matrix product, the weights, so plus the bias. So these two internal variables here, and we can do it by hand, and we check that this one by hand and linear, so they give the same. Okay, this is clear? Yeah.
It's not very clear to me how the activation function has a non-linearity to the procedure and why this is necessary.
I have to. I can give you a half answer now, and then I can find out something better. But nonlinearity is just because if you do like for instance, like you cut half of the value, no, I say some of the values, the negative values from the outputs. This is not something that you can do with a linear operation. So it's a nonlinearity. And why you need it mathematically? I know that if you only do linear operations on some input, you cannot take it to, you just can do certain amount of, certain effect on it. There would be this one of shifting it as it is, and like they say, rotate or make it a smaller dimension and shifting it. But you cannot really transform it into something with a completely other shape, like if you have a picture and a category of it is a cat or not. But so this is why linear doesn't work. Why linear is important, I have to find out more precisely answer, but that's the idea. It's just, yeah.
Does the activation function that you apply for each layer has to be exactly the same, or you can also apply different activation functions for each layer?
Huh. In principle, you can do whatever. You can construct your model, but now that you say it, I don't know if in practice it makes sense to mix them, or in practice the models they stick to one. Do you have?
Yeah, I just wanted to say that basically in the last layer, sometimes if you use a value activation function in the whole of your model, in the last layer you might want to use a different activation function to squeeze the input on a certain range. So for example, the tan h activation function gives you an output between -1 and 1. So if you normalize the data between -1 and 1, we'll see that tomorrow for generative models, you want to generate an output that is between -1 and 1. And for example, the other example is sigmoid activation function. If you want a probability, you have a number between 0 and 1, and so you will have to use a sigmoid activation function as the last activation function of your model. So that's the most common case of mixing.
Yeah, we can see it here, and so this is it for this notebook. But then we have an equivalent one. So remember this one, we put it, finish it in 1, and this one in principle, if you give a continuous input, it's capable of giving you a continuous output, because you know there is no per se discontinuity. And this one, we can use something like this for regression, okay? But I want to show you one for classification, and I think this is one of the cases what Rocco was explaining. Here, now let's say that the data is something that we're going to do later. We are classifying images that are pictures 28 by 28 pixels. So the data looks like this. And now here, pretty much looks the same. We have here the same operations, all the ReLUs, and actually left the values here the same. However, at the end, we don't finish like in this one. So we finish in a linear. But in this one, we are finishing in something called softmax. And softmax is a sort of an activation function. It's an activation function, actually, but it's used mostly, as Rocco explained, at the end. And the idea of it, I can jump to it quickly, since we're talking about it. Softmax is it's an activation function that you use it as well as normalization. So it has a shape like this, similar to sigmoid. But the idea of it is that, sorry, let me do a plot to explain. That, so if you this is your final layer, sorry, your final linear layer, it gives some values, can be negative, positive, whatever, because it doesn't have activation function. And then when you apply a softmax after it, you can you're going to normalize all these values in a way that they are going to be always positive, and the whole sum of them is going to be 1. So as a result, you can interpret it as a probability. So you can use this activation function, that to me, my mind is more like a normalization, but you can use this activation function at the end to train a model into giving you probabilities. And right now, if you have, like, let's say 10 classes, like in this case, I think they could be, for instance, identifying handwritten numbers that we're going to see in a minute. Then softmax, you can train it, so the meaning of this is going to be the probability of every handwritten number to be, number, like if it's something like this, to be a 3. Okay, and this is the main difference with regression. So in classification problems, in general, you have softmax at the end, so you can train it on probabilities. Is it clear? And since we are talking about that, the final notebook is this again a training. You will see it's pretty much the same that we did before with the linear model, but now we are actually doing this. The classification of handwritten numbers, and we are just going quickly over it because you will discuss most about it with Rocco later. We can download a data set of handwritten numbers that I will show right now how it looks. So it's images like this. They are 28 by 28. And here I put the values of each pixel, because here when we create the data set, we pass this transform, that is some utility of torch vision. It comes the same ecosystem of PyTorch. And we ask it to normalize and to convert it in PyTorch tensors. And at the end, as a result of this normalization, the values of the images are going to be between -1 and 1. So -1 will be, let's say, the white background, and close to 1 will be different degrees of shades that forms the number. And this is important to understand what the input data is in order to create the model. So we have this data set. We have, for the training, we have 6,000 examples, so 6,000 handwritten numbers, and 1,000 for the testing. And this time now we're going to do a quick testing to see how our model did during the training. And here, when you do this with Torch Vision, you get directly PyTorch datasets, and you can pass it to a data loader immediately. And here we set the batch size, and we can put, shuffles and drop last and whatever. And we do the same for the test. And we define the model, and it's the same model that we saw before. And notice that this it finishes in a linear layer, but this is only because the loss function that we are going to use, that is called cross entropy, internally in PyTorch, it applies the softmax. Okay, so we don't put the softmax here, but a softmax is being the last layer actually, because it's applied inside of the loss function. Is it clear? Okay. So we put the model in the device. You may get an error if you still have the kernel of the other notebook running. So you may come and do kernel in the other notebook, restart kernel, because the GPU won't let you to have two processes at the same time. And so we do like this. The cross entropy, I can explain in a bit what is it, but maybe we can leave it for later. Here we're going to use an optimizer that is called Adam, that you're going to discuss with Rocco a bit tomorrow. But it's a variant of a stochastic gradient descent that it brings enhancements to avoid having too much oscillation. So let's say it's going down, and when you have batches, it can oscillate like this, right? As you saw in the previous notebook. And Adam, well, it has some enhancements to make it not oscillate too much in the, let's say, the direction perpendicular to the gradients, but instead to kind of advance more, something like this, to make it more, to make it faster. And we put the learning rate here. I found out that it's 0.01, and in this case, it's more relevant, more sensitive. This is something in PyTorch that maybe we discuss later with Rocco. And the training looks exactly the same. We have epochs over the 60,000 images, and we're iterating over the train loader. And anytime we get an image, so we put the image and the labels. So if it is a picture of a 3 and a 3, the label, we set to 0 the automatic differentiation. We evaluate the model, get an output, pass it to the cross entropy. This output is going to be applied as softmax. So now we will have probabilities, and then it was going to compare the probabilities the model gave with the actual label. Like this thing has this I don't know, this set of probabilities, and is it the 3? Okay, the high probability is for 3, let's say. Let's check if the label is 3. If it's 3, it's good. If it is 4, it's not. And so of course it's a function. It's not like yes or no. Then back propagation, we get the gradients, and optimizer step move in the loss function. And history again is just for plotting. So we get 5 epochs, we can plot. So it looks like this. And as you see now, we don't have any other plot to check with the data because it's not possible. And so it looks like it converged. Maybe we can leave it more, but I think it's fine for the demo. And now in this part, we are going to use the model that is already trained, and we are going to test it in the test loader, so in data that it has never seen. And we are going to print the ratio between so right answers and the total answers that it will give. And this is called accuracy, and it's a metric that is very popular for classification. And it's giving us that 96.43% of the cases is getting right the number. And we can print some of the predictions for data that it has never seen. Apparently it takes some time. Okay. And so here is the numbers, and this is what the model put here, what the model has predicted. I think probably there are enough here that probably we can find some that they are not right, because it's 96% of the cases always. So in particular, if there is a number like kind of not very well written, it may not get it right. So this one it says it's 5. I don't even know what is it. Probably it's a 5 with some. And well, I print so many. Yeah. So that's it for this notebook. I can give you time, like I don't know, 5 minutes or so before we go out. But do you have any questions you would like to discuss? Can you see the similarity with the previous notebook, at least? No? Yes, no. Okay. Yeah, I hope you see, because the steps are the same. It's just to get the data. The other one, we define it ourselves. This one, we read it. We make a data loader. We selected a model that we wrote it ourselves. We selected a loss function. In this case, it's cross entropy that is used for classification. And we got an optimizer. Before we use stochastic gradient descent, but now we use Adam, which is an improvement over stochastic gradient descent. But the reason is pretty much the same. And finally, we do a training loop over epochs and training and batches. And the steps are really the same. So initialize the automatic differentiation, evaluate the model, get a prediction, compare it pass it to the loss function and compare it to the data, get the gradients, and move in the advance in the minimization. And so this one looks pretty much the same. So we see how the loss converges through the steps. And in this case, we did validation. And as I said before, the validation, you can do it also always at the same that we did here, this 96%. We could do it inside of the loops. You can always test in new data and see how the accuracy increases at the same time that the loss is decreasing on the training data. Is it clear? Yeah.
So this is what you call the unsupervised training.
No, supervised. Supervised is when there are pairs of data, like image and label, like this. Yeah. We have 3, and it comes with so this picture of a 3 and a 3, and we can have a loss function that we can compare if the output is what the label is. Unsupervised would be like there are no labels, and maybe we have a task to define how many different numbers are in this set, and the model can check, okay, based on the shapes, I can group like all the ones that look like this are 3s, and all the ones that are like this are 0s. That would be unsupervised. Okay, then we can go for lunch, and now in the afternoon you're going to continue with Rocco with convolutional neural networks, and yeah, this is the, like they say, the go-to model when working with images and computer vision in general. And you will see later that this is a model that already has, besides these layers that we saw here, so the linears and the activation functions, it has a different another type of layer that it helps to the model to understand, to extract more information from the images. Okay, the rest is going to be the same. Yes.
Hello. So the last output vector is 10 dimensions. Is that, goes from, tells you from 1 to 10 which number is? Is it like a one-shot thing? Like the hot-shot thing?
Yeah,
that is,
this 10 is whatever numbers. It's just come from, so you put the image and you do many linear, relus, and at the end you get a number, a real number. And it's something that is going to look like, they're 10 numbers, but they can be anything, can be negative, positive. So these numbers inside of the loss function, the cross-entropy loss function, because of implementation, they are going to be applied as softmax, and they are going to be converted in probabilities. So now these numbers, they are going to be converted in something that is between 0 and 1, and all of them sum to 1. And the cross-entropy, what this does is to check if, to compare it, let's say that one sample is a 3 with the label 3. And the model is going to give you something like this. In this case, let's say it gives you a 1. And the cross-entropy loss is going to check, okay, if the model, the highest probability is what the label is saying. And if it is not, this is not going to, it means that the model didn't predict this one well. If it is the same, it means that the model predicted well. Is it clear?
So before starting discussing about convolutional neural network, which is the main topic of the next session, we wanted to go a bit more slowly on the notebook that we've seen before, because it's also the basis for what we'll be doing with convolutional neural network. So essentially at the beginning, what we want to do here is image classification with MNIST data. MNIST is a data set of handwritten digits, as we have seen already. And in the first cell, we just load all the things that we need. And an important thing to notice here is the torch vision. Can you see, or do you want it a bit bigger? Is it okay? Yeah. Something interesting is this torch vision module that is provided together with PyTorch, and has some utilities to work with images and computer vision tasks in general. What you can do with the torch vision data set is that you can load pre-made data set that are automatically downloaded from the internet, and there is a whole bunch of them, and they're usually standard data set used to test and train computer vision models. And you can just do dataset.mnist. Mnist is the name of the dataset that we want to use. Say where you want to put the data locally on your machine. You can say if you want the training or the test set, because usually they're already pre-split in a training set and a test set downloaded. And then the transform is quite important. We will see it again tomorrow to do something that is called data augmentation. But for now, we only use the transform to essentially transform images that are stored in the image format that Python uses, that is called PIL, and to transform them in PyTorch tensors. And they're usually between 0 and 1 in values. And so we do also a normalization that removes 0.5 and divides by 0.5, so we get a range from -1 to 1. And you can look, if you run this cell, it downloads the data set, and you can look at the data set. There are 16,000 examples in the training data set, and you can see also the transform that is associated to this data set. Same for the test set. And here we can show like one example of the image. We have seen this before. And then when we have this data set, we can define PyTorch data loader, which is a class that essentially is what you use to iterate over mini batches during training. And the data loader, you pass in your data set. So we have 2 data loaders, one for the training set, one for the test set, and you can choose the batch size. For the training set, the batch size is very important, as we have seen this morning. It's an hyperparameter of your model. For the test set, you can use whatever fits in memory because you're not computing gradients anymore, so it doesn't really matter. Then you can do the shuffling through, which means that every time you load, you do an epoch, the examples in the different batches are shuffled. So they're not presented to the model always in the same order, but they're randomly shuffled. And again, for the test set, you don't care about this shuffling, so you don't do it. And drop last is what we have seen before. So we can just run it, and we have so the train loader and the test loader that we can use during training. And then something important here is how the models are defined in PyTorch, but essentially you always subclass from the NN module class, which is essentially the base PyTorch module. All the linear layers, ReLU, everything is subclassed from this class. And this class essentially has some functionality behind, and one of the main functionalities that register all the other modules that you define. And you can define, you have to initialize the superclass, so with the standard Python, and then you can define linear, ReLU, linear, ReLU, and linear again. And you can define these as members of this class in the init method, that is the constructor of Python. And then what you need to do as well is to define the forward function. This is how the data is propagated into your neural network. So in the forward function here, since we have a linear layer, we take the images that are matrices of 28 by 28 pixels, and we flatten into a one-dimensional vector. And this is what the view, tensor.view is doing. And then you can just propagate this reshaped tensor into your network and get it through the first linear layer, first activation, second linear layer, second activation, and then you get the output and you return it. And so this is how you define a model in PyTorch. This is the most common way. You just subclass for the NN module, and then you define the layers that you want in the init method, and then the forward pass. And the backward pass, you don't have to define it because it's automatically computed by PyTorch autograd. So that comes for free, essentially. And one of the cool things that this class does is that it registers all the parameters, and if you print the model, it will actually show you the layers that you defined in the way that they're used in the forward pass. So you have a fully connected layer 1, ReLU, fully connected ReLU, and fully connected. And this comes from, this printing of the model comes from free because we subclass from the module class. Yeah.
I have a question about how you design the model in the sense how you choose the activation functions for each layer. Is it more on a trial and error basis?
I mean, what I usually suggest to do is to look at similar architecture and similar paper that do what you want to do. But in general, yes, this is like the model itself. You have to decide how to define it, and it's all like an hyperparameter if you want. Because the actual parameter that you optimize are the weights inside the linear layers. But then how many linear layers you want, which kind of activation function, that's something you have to test. So in that sense, finding the right model is very empirical. Yeah. Yes, so essentially this is the way you usually define PyTorch models, and you can go crazy with the forward function and define very complicated models. And then you can also define like sub parts of the model as NN modules, like a block of your model, and then reuse that in more complicated models. So you can really separate the concerns. And for example, this is what happens to the linear model. The linear model is itself an NN module that is defined within PyTorch, and then you can use it within your own NN module class. And then for classification, we use the cross-entropy loss. And the reason why we use the cross-entropy loss is essentially the loss that is good for classification tasks, and is a loss function that uses the class probability that are output of your model. Actually, they're computed internally, but you can see it as a loss function that penalizes misclassified example. You don't want to use the mean square error loss on the probability, for example, because you don't really care that your probability is 100% for the right class, even if it's 80%, but it's still producing the right class. That's something that is good for you, while the other is also true. If the model is producing 80% as a misclassified example as probability, then you want to penalize it a lot because it's just not. It's very confident that the prediction is correct with 80% probability, but then it's wrong, and so you want to penalize that more. And this cross-entropy loss, essentially, it's designed in this way. Then optimizer. This also we skipped a bit this morning, but essentially there are some layers that have different behaviors when you train the model and when you do inference, when you actually use the model to do prediction. And so you need to ensure to put the model in training mode before training. And then everything else, I think it was covered pretty well already. Do you have a question about the training loop? Yeah.
Explain what you meant by the cross-entropy thing again. You said if you use just a linear least squares kind of fit,
Yeah.
then it doesn't adapt well to certain properties. Is that what you're saying?
Yeah, exactly. Like it's not the right loss function for a classification. Yeah. It's,
How many loss? I mean, there are tons of loss functions. Is there like a dictionary of them anywhere?
yeah, I mean, they're all defined in the NN module, but usually in this class, at least, we only see the cross-entropy and MSE loss, mean square error. But yeah, you can, for example, use also the absolute error loss, or there are other loss functions. Or you can also design specific loss functions. Actually, in the generative model part, we will see some specific loss functions that are a bit more fiddly.
When you become expert at this, you learn rules of thumb of which loss functions.
Yeah. But I mean, for classification, it's always the cross-entropy loss, essentially. Yeah. Do you have questions on the training loop? Yeah. Oh, yeah, for sure. Also.
Just a curiosity, where you said the limit is from 0 to 1, and it says you scale from -1 to 1.
Mm-hmm.
Why is
This is a very good question, but essentially it's to reduce the data skewness of your data because the optimization depends on the shape of your loss function. That also depends on the shape of your data. So for example, in the data set that you had a very round loss function, but you can think about if you have like very different data, like the range of the data is very high, you have like, for example, elongated shape, and so it takes more time to actually reach the minimum. So essentially it's to have the data distributed around 0 and in small values that simplifies the optimization problem. We can maybe modify later on the notebook and to show like a loss function that is not it's not like a round, a parabola essentially, but is skewed. Does it answer your question? Yeah. Okay.
Related to that, is if you had input data which was not an image, but it was somehow distributed according to, let's say, a logarithmic, would you take the log of the data before running it through the model, or would that somehow distort the way the model actually, because you'd be
well, it depends. There are some layers that do the normalization internally and then also learn it, and we will see them later. So if you use this kind of layers, usually you don't need to normalize, but in general, yeah,
instead of having a layer of perceptrons, you could have a layer of normalization.
Yeah, you can have that as well. Yeah.
You can stick anything in.
Basically, yeah. Because of the autograd, basically yes, because then the gradients are computed automatically, so you can just define, oh, I want to normalize in this way. You do the normalization, and that's being added to your computational graph, and then you can compute the gradients because you have autograd, and so basically, yes, you can stick any function in there. Yeah. Do you have any other question about this notebook? Well, I mean, we can finish it, but there is the training loop, and I think this was explained at length, so maybe we don't need to go through it again. And then you can plot the loss function. Well, actually, it takes a bit to train. Well, while it's training, we can plot the loss as you've seen before, and maybe when you test the model, the interesting thing to notice is, again, that you put the model, before we put the model in training mode, because I said that none of the layers used here actually have this problem, but later on we will see some layers that have a different behavior during training and during inference, and so we put the model in, where is it? In training mode, but then when we do the testing, we have to put it in evaluation mode, so that essentially these layers that behave differently behave in the correct way for training. Yeah, and then here is essentially the same thing. Well, you get the output of the, you get the output of the model, you pass the input, you get the output. And by the way, you can call the model, and you should call the model, because the NN modules class defines the call function, the Python call function, so you can actually call the model like this on the data. You don't have to explicitly call the forward function, but you can just call the whole model. And actually, you should do it this way. And then you compute the class probability. And then from the class probabilities, there is just a softmax of the output, as we have explained before. You can get the predicted label as the arc maximum of this probability. So it's essentially it's the element of the probability vector with the highest probability, which is your prediction. And last thing maybe worth mentioning is this Torch autograd context manager, which essentially says to PyTorch, ignore all the gradients, don't compute and don't keep track of the computational graph. This reduces a bit the computational load of the forward pass, and is used during inference because you don't need to train the model. Like, we are not training the models anymore, so we don't need the gradients of the loss function, and so we can speed up things a bit. That's a good question. Probably it's because how autograd works. I don't know. Yeah, I would assume that the model is completely like separate from autograd. That is, they do not interact. They interact only through the tensor that you pass through the model, and so probably this torsionograd say to the autograd engine not to care about the forward pass, but it has not much to do with the model, I think. Yeah. Do you have any other question about this notebook? Is it clear?
Just one thing, I missed earlier when you said you're referencing the drop last.
Yes. So essentially, when you divide your data set in batches, it might be that the size of the data set is actually often the case, is that the size of the data set is not a multiple of the batch size. So you have a lot of batch sizes, well, all of them -1 of size 256, but the last batch will contain what's left. Maybe there are 3 images left on the batch, and so you will have the last batch with 3 examples. You can keep it, but usually it's simple to just drop it. And because of the shuffle, usually that example will still be seen by the model because you reshuffle, and so the batch that you drop will be always different, and so you don't really lose anything. Do you have other questions about this? No? Clear, not clear? Yeah?
Relevant that I define a batch size for the test data because I actually don't need to accumulate the gradient for the batch size.
Yeah, but you still have like the tensor of, so your input will be a tensor of all the images for the batch. And so at some point you will hit memory limitations. For example, here we have, maybe not with this data set, I didn't do the calculation, but we have 60,000 examples. 10,000 for the test set. So your tensor will be 10,000 times 28, times 28 numbers.
Inference mode, it will always produce the result in this batch size.
Yes, yeah. And as I mentioned, you can make it bigger because it's not a hyperparameter anymore. It doesn't affect your model, while the batch size on the training set, as we have seen this morning, really affects the training. But in this case, you can essentially choose the bigger number that fits in memory. But you're still passing, the way PyTorch is constructed is that you're passing a whole batch to your model. And you can see it here in this view function. The first dimension, we know the dimension of one image, but we don't know how many images are passed. So when we do the reshaping, we pass -1 so that it reshapes the 28 by 28 images for every batch dimension. So essentially, this is very general and say, if I pass a batch of size 3, this view will be 3, 28 times 28. And if I pass a batch size of 10, this will work as well. And the reshape would be a tensor of size 10 and 28 times 28. Yeah. And sometimes you can hardcode this. This is why the drop last is equal true is quite important sometimes, because sometimes, also in the later notebooks, it's a bit easier to track the dimensions, so you can do drop last equal true, and then if you want, just like hard code your batch size in the first dimension. Then, of course, if you change it here, you have to change it here as well. But, the -1 is a very convenient way of saying, I don't care how many batches, I just know that the last dimension has to be 28 by 28.
Why is shuffling goes through for the train loader and shuffling goes false for the test loader?
Because you don't care about shuffling when you're testing. because you're just computing the predictions for all your test images. So you don't care in which order they are in the batch. While during training, well, the model can actually start to use that information. If you have, I don't know, dogs and cats, for example, in your batch size, and they're ordered, so you have like 10 images of dogs and 10 images of cats, and they're always ordered, the model might be able to exploit this information and just say, oh, this is the first part of the batch, so it's a dog, and this is the second part of the batch, and it's a cat. So it can exploit this information. By shuffling, you prevent this from happening. But then when you're testing, you don't care because the model is already trained. Yeah.
You deal with the case where you don't know how many features are entering, like if you have images of different size?
You can sort of, in the sense that with images, well, with the linear model, no. You need to know the size of the input. With the convolutions, yes, because they work differently, and we will discuss about them shortly. But essentially, the dimension of the image doesn't enter anymore the definition of the convolutional layer. It's a different layer. And so in theory, you can use it for different sized images. There is still a problem, like if you go to images that are much smaller, because if you decrease the size, for example, here we are going from 128 to 64 features and from 64 to 10. But then if your initial image is much smaller, when you reduce the size at the end, you will have like 1, or like it doesn't work with the dimension anymore because you reduce the size too much. But usually a bit bigger or a bit smaller works. And there are layers where you can, well, we discussed that later, but there are layers where you can essentially set the output so that the last output, you fix it. And so if you have different images beforehand, then the output of one specific layer will be always the same size. And so then everything, it doesn't destroy everything that follows. Yeah?
Second question, how robust is it to missing data? Like, of course, here we always have pixels everywhere, but for some data sets, we might have a missing value. Is there any recommendation? Like, how do you insert something else?
I mean, what do you mean missing values? Like on the data set?
Yeah,
like you don't have the label?
Imagine that one pixel is missing.
Well, there are many techniques to do that. For example, if you mention that one pixel is missing, I would take the average of the neighboring pixels or something like that. Or you can do an interpolation and just fill that missing pixel with something reasonable. So yeah, you can do that. I mean, it can probably, if it's only one missing pixel, it can probably still works because of how the convolution works. I mean, missing would be that is a 0, right? Like if you put a none, it will fail. Okay, yeah, in that sense. So you have to essentially pre-process your data to remove nuns if you want.